Good afternoon, everyone. I would like to start section 4. And the chair will be Professor Gustavo Ayala from University of Mexico. And the co-chair of this section will be Jelena Milosevic, Ilic, from Instituto Superior Te, Portugal. You may start when you are ready.
Good afternoon. Good afternoon to everybody. It's an honor for me to chair this session and also to welcome Dr. Jelena Milosevic as my chairwoman in this session. And we having 5 presentations, and I will, to shorten the times, I will give the voice to the first presenter. That would be the paper of seismic response of irregular buildings with rocking piers. And in principle, I think it would be presented by Ioannis Thomaidis from the City University in London, I believe. So please, could you start, Doctor?
Yeah, thank you very much. Hello. Sorry about that. As said, my name is Ioannis Thomaidis, and I will present to you. Initially, thank you very much for attending this presentation. I will present to you a topic related to the seismic response of irregular bridges with rocking piers. This is part of my thesis that I recently submitted at City University of London under the supervision of Professor Andreas Kappos and Dr. Alfredo Camara. So the layout of today's presentations, I will start with some principles of rocking pier isolation. Then I will pass to the analytical formulation of a bridge with rocking piers by describing 3 conditions: rocking initiation, equation of motion, and the impact problem. I will then pass to the seismic performance of bridges with rocking piers, with emphasis on bridges with different degrees of irregularity, and I will close this presentation with the conclusions. To begin with, the concept of rocking pier isolation, although quite recent, it was proposed quite recently as a promising alternative for earthquake-resistant bridges. It dates back to ancient times when ancient builders, without having the ability to construct integral joints, they used rocking surfaces between the adjacent members. 2 characteristic examples are the Stonehenge in the UK and several ancient temples in the Mediterranean, like the Temple of Apollo in Greece. The structural advantages of these configurations that they manage to face the test of time are mainly 2. The first one is their negative stiffness. So in principle, resonance is not possible to occur. But also practically this is not feasible to happen, as was shown in previous studies. And the second one is that the restoring mechanisms derive from the physical properties of mass and mass moment of inertia. From the analytical point of view, the first one who examined analytically a rocking structure was Hausner in 1963, who examined a freestanding rocking block. 5 decades later, Makris and Vasiliou presented the corresponding frame system, a regular frame system, or in other words, a rocking frame with columns of same section and height. And a few years later, Dimitrakopoulos and Ioannis presented the corresponding irregular configuration, which consists of 2 piers of same section but different height. Quite recently, we presented the corresponding bridge, a regular bridge with rocking piers that takes into account the contribution of the abutment backfill system through a spring and dashpot element that work in parallel at both ends, as well as it takes into account some additional parameters like the joint gap between the abutment back wall and the superstructure, and different span arrangements for a more realistic bridge configuration. Today, I'm going to present the corresponding irregular system that consists of 2 rocking piers of same section but different height, and takes into account also the effect of the abutment backfill system. In order to formulate the movement of this bridge structure, some assumptions need to be made. The first one is that we ignore the deformability of all the structural members, and the second one is that we don't expect sliding effects at any instant. The rocking motion of this configuration, in order to describe the rocking motion of this configuration, three conditions need to be described. The first one is rocking initiation, or in other words, when does the system enter rocking motion? The second one is the equation of motion, or what happens as soon as rocking motion has started. And the third one is the impact problem, that describes what happens when the bridge returns to the at-rest position, impacts at the corresponding pivot points, and then reverses the rocking rotation to the other direction. In the following slides, I'm going to present these three conditions, but with emphasis on the difference between the regular bridge structure and the irregular one. So for the rocking initiation, the application of virtual work is applied that results in an equation of this form, where the minimum ground acceleration that is capable of inducing rocking motion is equal to a constant lambda times the gravitational acceleration times tangent alpha, where alpha is the slenderness of the rocking piers. For the regular system, lambda is equal to 1, so the expression to describe rocking initiation is quite simple. While on the other hand, for the irregular system, lambda has the form presented, showing that the equation is much more complex, and in addition, there is a double sign formulation that indicates that the ground motion that is capable of inducing rocking motion needs to have a different value depending on the direction of the movement. On the bright side, though, the equation of lambda for the irregular system is greater than 1. That indicates a delay in the initiation of rocking motion for the irregular structure compared to the regular one. For the equation of motion, the Lagrangian equation is used, resulting in the equation shown for the regular system. Although at first glance it seems a bit complicated, it's not that much, and I'm going to try to explain it. So the angular acceleration of the rocking piers is equal to two terms, frame system and abutment backfill contribution. The frame system describes what happens before contact with the abutment backfill system, while when this contact is activated, the term abutment backfill contribution is integrated in the equation of motion. In both terms, in general, we can see some familiar terms, like alpha, which is the slenderness, like P, which is a constant which describes the piers, and so on and so forth. And also in the abutment backfill contribution, we can see the spring stiffness and the dashpot coefficient. The corresponding equation for the irregular structure, it presents again two terms, the term frame system and the term abutment backfill contribution. Again, there are some familiar terms like R1, K, and C. But in general, we can conclude that the expression for the equation of motion for the irregular structure is much more complex than that for the regular one. Additionally, intentionally, I didn't mention about the parameter Q. Q is a factor of the term abutment backfill contribution, and in fact, it is a multiplier of the effect of the spring and the dashpot element of the abutment backfill system. In general, larger values of Q indicate higher contribution of the abutment backfill system in the rocking response, which was found to be beneficial in terms of seismic response. So in the next slide, we show what is the value of Q for different degrees of irregularity. In general, we can see that highly irregular systems, systems with higher irregularity, show higher values of Q, which is beneficial in terms of seismic response compared to regular ones that show lower values. The third condition is the impact problem. For the impact problem, an impulse formulation is used using the usual concept of coefficient of restitution. Coefficient of restitution is a constant that relates the velocity after the impact to that before the impact, and in order to express attenuation of movement should be lower than 1. So lower values of eta mean higher energy of dissipation, higher energy dissipation at each impact. The expression for the regular system is the one that's shown at the top. We can see that there are some familiar terms in this expression, like the slenderness and the constant gamma, which expresses the effect of the superstructure, as well as a parameter lambda dash, which expresses the span arrangement. On the other hand, the corresponding expression for the irregular system is much more complex, way too long for the system. And there is also a double sign formulation which explains different attenuation of motion when the rotation changes from counterclockwise to clockwise and vice versa. Again, in this graph, we can see the value of eta with respect to different degrees of irregularity. We can see that regular systems show higher values of eta, so lower energy dissipation at each impact, compared to highly irregular systems that show lower values of eta. This means, this insinuates actually a greater seismic performance. So overall, although the irregular system shows higher complexity in terms of the dynamics, it insinuates from some parameters higher stability, greater seismic performance. Now, the seismic performance is examined with emphasis on different degrees of irregularity. 3 different bridge structures are examined. In all these 3 configurations, the superstructure and the abutment backfill contribution is the same, and we only change the substructure. Specifically, we examine 2 rocking piers for the regular system with same height of 26 meters, and we decrease the height of one of the 2 piers in order to have a moderately irregular system and a highly irregular system, respectively. The seismic performance is examined with 10 artificial ground motions that match the Eurocode 8 spectrum with PG 8.6G. Now, passing to the results are presented in terms of peak responses. The black graphs are for the regular system, the red one for the moderately irregular, and the green one for the highly irregular. The first graph shows the longitudinal displacement of the superstructure. In general, we can see that this is not affected considerably, so the seismic performance is more or less the same, independently of the degree of irregularity. But the second graph shows the vertical displacements of the superstructure, which shows that the more irregular the configuration, the higher is the deck uplift. This can be explained by the following 3 graphs that show that the irregular system experiences some deck rotations that are not present for the regular system. And this is due to the different rotation of the rocking piers, θ1 and θ2. For θ1, the rotations are more or less the same for the different systems, but θ2, it refers to the pier that we change its height. We can see that the shorter the pier, the higher is its rotation. To sum up, from the dynamics point of view, the equations are much more complex for the irregular configuration. However, this is not be related to a corresponding finite element numerical analysis, while the simulation that will be followed will be pretty much the same for a regular and an irregular system. But the irregular configuration shows delayed rocking initiation, higher contribution of the abandoned backfill system, and higher energy dissipation at its impact at the rocking interfaces. The seismic, with respect to the seismic performance, the activation of the predominant failure mode of the system is not affected by irregularity, but the irregular structures experience a different rotation of the rocking piers and different uplift, leading the superstructure to rotate and therefore uplift more compared to an irregular regular system. To close, it should be noted that all the rocking configurations survived strong ground motions of PGA 0.6G with a reserve capacity of 50%, which is quite high. Thank you very much for your attention, and would be really grateful for any questions.
Thank you very much for your presentation. I think we have one question with Professor Andreas Kappos and Professor Rita Bento.
So who is starting? Professor Kappos?
Yes.
Yeah, okay, now I can unmute myself. I said that I have no question because anyway, I am a co-author, but I do have a comment or perhaps you were wondering what is the purpose of going into all these very complex formulation as opposed to doing something more straightforward, like for example, a finite element analysis. This would be a very legitimate question. And the truth is that in finite element analysis, the regular and the irregular configuration would have been treated in essentially the same way. And there is no this additional complexity that you have seen in the analytical formulation. On the other hand, the cost of analysis for problems involving contact and impact is so huge in, let's say, standard finite element analysis, although it is not standard, in fact, it is advanced type of finite element analysis, that I am finally convinced that it is worth exploring also the analytical as opposed to the numerical approach. Thank you.
Thank you.
The question is just about the type of results that you reach. Basically, even for very irregular structures, you conclude that you don't have much damage. They survive for a very high intense seismic action, 0.6G, I believe. It's something that you are expecting according to what we have observed in past earthquakes. I'm not aware about this, just asking. So it's something that you are in fact expecting for this type of bridges and for this type of irregularities?
Anyway, regarding the seismic performance, again, could you say again your question, because
if you are expecting this type of behavior if for such a high level of seismic action that you have considered 0.6G, yeah? So
if we were expecting, no, actually we weren't expecting that high seismic performance to withstand so strong ground motions, and this was surprisingly for rocking structures. I believe this would be an advantage of rocking structures compared to conventionally designed structures.
okay, very nice, interesting, thank you.
We have one more question. Professor Oren Lavan, please.
So it's not really a question, just in addition to what Professor Kappos was saying, formulating the analytical, taking the analytical approach essentially also enables the identification of the controlling parameters of the system, which is something that could not be done with finite elements, or could not be done easily with finite elements. But with the analytical formulation, it's very easy to identify the controlling parameters of the system, and this is another advantage. Yeah,
and this is something I think that I tried to pass through the presentation, that we know beforehand some parameters that may govern the seismic response of the structure. And actually, this was shown in terms of seismic response.
Okay. Thank you very much. The second presentation will be retrofitting of irregular structures for seismic loads using rocking walls, presented by Ameer Marzok from Israel Institute of Technology.
Thank you. My name is Ameer Marzok, and I'm a PhD candidate from the Technion Israel Institute of Technology under the supervision of Professor Lavan. My presentation is in the topic of retrofitting of irregular structures for seismic loads using rocking walls. So the presentation includes a short motivation, and then the concept of rocking walls will be briefly presented. After that is a case study of retrofitting of irregular frame structure using base rocking wall will be discussed. And this will be expanded to introduce the solution of multiple rocking walls for the retrofit of irregular frame buildings. So today it's common to design buildings to dissipate the seismic energy based on plasticity of the primary structural elements. This plasticity means large damage, which in turn causes a large economic loss after the seismic event. In addition, if we look at the force deformation curve that is schematically shown here in the figure, we know that if we reach the plastic deformation, then removing the load will cause large residual deformations. The problem with these large residual deformations that they are very hard to fix, and sometimes it's impossible or economically prohibitive. So to solve these problems, self-centering systems were proposed. The advantage of these systems that they can significantly reduce the residual deformations. And in addition, they can be designed such that the energy dissipation is achieved by designing special devices that are located in previously known locations in the structural system. The behavior or the force deformation behavior of these systems is referred to as flag-shaped behavior, which is shown here schematically in the figure. The special thing with this force deformation curve that it passes through the origin, or in other words, zero force gives zero displacement. So several types of systems were proposed to achieve this type of behavior. This includes rocking walls or rocking concentrically braced frame, which in the macro level, they behave the same. Post-tensioned frames and systems that use special self-centering devices. The advantage of a rocking wall that they have a large lateral stiffness, which for irregular structures or frame structures, it helps to regulate the interstory drift along with the building height. So the concept of rocking walls, if we look at the behavior, it's a combination of two behaviors. The first one is the rocking itself plus the pre-stressing tendon, which gives elastic nonlinear behavior. We add to this energy dissipation from the energy dissipation device. If we combine these two behaviors and tune them correctly, we can potentially achieve the desired flag-shaped behavior. So in this study, we will use a rocking wall in order to retrofit an irregular steel moment resisting frame. And then we will add the multiple rocking solution in order to reduce the demands at the rocking system. So the case study includes a 14-story building that is a steel moment resisting frame that has a setback level that is located at the 3rd floor of the building. The building is subjected to a set of ground accelerations from the LA ensemble, which their acceleration and displacement spectra are represented here in the figure. the first natural period of the structure is 1.94. So the analysis of the frame were conducted using the finite element software OpenSeas, using nonlinear beam and column elements, which were modeled using the fiber element section method with 5 integration points along each member. The P delta effects were also considered, and elastoplastic behavior with 0.5% hardening was considered. The bare frame results show large interstory drifts, which are presented here along with the building height. Each gray line represents the results for a single earthquake, and the average is represented by the black line. The red dashed line here represents the setback level. And in addition, if we look at the roof displacement, we can see that the residual displacements in this case are about 30 centimeters, which gives an inclination angle that is 0.006 or more than that, where previous studies have defined an allowed inclination of 0.005. So in order to reduce these residual displacements and interstory drifts, we have added a rocking section to this frame. The rocking section of the rocking wall was designed using a reduction factor of approximately 6. Other reduction factors were also considered, but this value have given the best results in terms of residual deformations. So the natural period of the building was shortly or slightly decreased because we have added a stiffness to the building. So the model of the rocking wall is presented here in the figure. This figure shows a numeric model for OpenSeas, which is for multiple rocking wall, which we will use later. But the concept is the same also for base rocking wall. I will not go here into details for each one of the elements, but the important thing here is that we assume that the rocking behavior is located at the edge of the rocking walls, which in macro modeling can be suitable to achieve good approximate results. So the results of the structure that is retrofitted with a base rocking wall are represented here in this slide. The left figure shows that the interstory drifts were highly regulated along with the building height, and they are significantly reduced. The middle figure shows that there is a reduction in the residual displacements. There are still some residual displacements which are caused by the nonlinearity of the existing frame itself. The right figure here shows the peak moments at each section of the added rocking wall. And we see that these moment demands can be large along with the structure height. So we are interested to reduce this moment envelope. To do so, we designed a multiple rocking section. Multiple rocking walls were originally proposed for in order to reduce the higher vibration mode effects. If we look schematically at a moment envelope of a rocking wall with base rocking, including the higher mode effects, we see the bending moment diagram in the right. So if we add another rocking section along with the building height, additional to the one that is located at the base, we can reduce this moment design envelope. And with this, we get increased interstory drifts. So to design this type of system with, in order to retrofit our irregular frame, we ask ourselves where to locate the additional rocking section, and in addition to which decomposition moment to design for. The decomposition moment is the is the moment in which the rocking behavior starts. So we have conducted a parametric study where each combination of these two parameters was subjected to nonlinear time history analysis, as explained before. And the results are presented here in the contour maps. The left figure here shows the maximum interstory drifts of the multiple rocking system normalized with the bare frame. Just for reference, the results for the base rocking system shows a value of this of 0.43, which says that the multiple rocking solution increases always the displacement as we expected before. The vertical axis here represents the additional rocking level, and the black line represents the setback level of the building. The horizontal axis here represents the ratio between the top to the base decomposition moments. The right figure shows the volume of the moment envelope. And we have selected the marked point here to examine the behavior of this system. So this point represents a rocking wall with two rocking sections, where the second one is located at the setback level or at the third level of the structure. And as we see here, the reduction in the moment envelope volume, as we see in the right figure here, can be significantly reduced, while the interstory drifts, as we see in the left figure, are slightly increased. The response of the selected points, is shown here for interstory drifts, average peak moments, and roof displacements. What's interesting here is that the roof displacements, the residual deformations, are similar to that received with base rocking solution. And here the results are compared for each one of the systems. The red line represents the bare frame, and the black and blue line represents the base and multiple rocking solutions, respectively. And we see that they look alike with in terms of interstory drifts, while they significantly reduce the average moment demand. And the right figure shows that the residual deformations, as we wanted, were significantly reduced. So to conclude, the behavior of irregular steer moment resisting frame with multiple rocking wall system was investigated. The effect of the location of the design and the design moment of the top rocking section have been examined. The results show that traditional base rocking solution regulates the interstory drifts and reduces them. And adding a rocking section at higher level could potentially reduce the bending moment envelope. And in the presented case study, a reduction of approximately 29% in the bending moment design envelope was achieved, while the interstory drifts were increased just by approximately 9%. Thank you for your attention.
Thank you very much for your presentation. Some question? Professor Rita Bento has one question, please.
Yes, so congratulations for the work. Very clear, the presentation, very clear what we have been doing. So I have several questions, in fact, because I have a group working in the seismic assessment of reinforced concrete buildings, quite curious about different retrofitting solutions. So my first question is, how did you evaluate the residual displacement at the time of it was after the record finished, or it was exactly the instant where did you evaluate the residual deformations? So it's basically just a much technical question. Another thing is, do you believe that it should be a solution to retrofitting current residential buildings? Did you ever perform cost benefit analysis? Any ideas about costs of implementing this type of retrofitting solutions?
Okay, so thank you for your questions. About the first question, which deals with the residual deformations, there are several ways to calculate them, but in this case, we selected the value that at the end of as the average results of the sequence of the response at the last 10 seconds of the history of the record. Regarding this system as a solution for the retrofit, it has many advantages. In economic, I haven't examined this, but as we know, this system has small residual deformations, which sometimes cannot be fixed if we have them after a seismic event. In addition, they can be designed such that the energy dissipation can be, in these elements, can be replaced after the seismic event, which is believed that it can reduce the loss after the seismic event.
Okay, thank you.
Thank you very much. We have one more question. Maria Vittoria, please.
Well, first of all, congrats on your research. I think that it was very interesting and accurate. I have some quick question and something just to make you think, because I'm actually studying the retrofitting of reinforced concrete buildings. My first question is related to the numerical modeling that you have followed. I've seen that you have used the OpenSea software. And the question is that the wall was modeled with precast concrete, I think, or right? Okay, perfect. And then you use pre-stressed tendon, which is modeled with steel. I just wanted to know how you simulated the interaction between both elements, because I think that I didn't understand. Have you used, I don't know, because I haven't tested this kind of retrofitting solution. Maybe what I've been thinking from your presentation is that you have used some kind of shell element or.
Yeah, I understand your question. If I can share again my screen, then it will be easier to explain how I model this. Yeah, so this is the model that we have used for the analysis. Okay, so the concrete wall is expected to remain elastic using the capacity design philosophy, because we do all this solution because we want to concentrate the damage in a place that we know before the seismic event. So the wall itself is the elastic Timoshenko beam that is presented here. And from outer point, we can connect the rocking section with a cable element. And the width of the rocking is represented by these stiff beams, which has a gap element that is located at the corner where we assume that the rocking angle is develops.
Okay, okay.
I hope this was clear.
No, super interesting and super complicated. And just to finish something, to try to be quick. I think that in your study, Kate, the most vulnerable part is the connection between the taller parts and the smaller part of the building. And actually, here in Spain, according to the construction and the structural codes, structural joint will be needed in that part. So I don't know. I might suggest you to perform, I don't know, different sensitivity analysis to see which is the most profitable location of that retrofitting element. And this is related to the idea that Professor Rita was sharing with you. So thank you and congrats.
Thank you.
Thank you very much. Okay, next presentation actually is mine presentation, so I am going to present. Okay, I'm going to present work of our master student, Seismic Retrofitting of Irregular Mixed Masonry Reinforced Concrete Buildings in Lisbon. There are 4 types of old masonry buildings in Lisbon: pre-pombalino, pombalino, gaileiros, and mixed masonry reinforced concrete buildings, which are going to be case study, which I'm going to present now. As we can see here, this is the area where these buildings are located in Lisbon. In area is called Alvalade, and then present the 30% of building stock in Lisbon of all masonry buildings. In these buildings, reinforced concrete was introduced for the first time. And then, as all old masonry buildings, they were built without using any seismic code. After some analysis, we concluded that they have high level of degradation and deterioration of structural materials, and due to the fact they're still used for housing and services, some seismic risk analysis at the territorial scale should be performed, and eventually after that, some appropriate strengthening techniques should be proposed. This is in total, there's around 1,300 mixed masonry reinforced concrete buildings in this Alvalade neighborhood. We analyze about 33%. And after analysis, we concluded that they have very low resistance to seismic action, and most of them show heavy or very heavy damage. And due to this, and due to the fact that based on statistics from 2011, in these buildings live around 32 inhabitants, these buildings should be reassessed and strengthened. This is short outline about my presentation: characterization of the case study building, some global seismic behavior, strengthening techniques which we propose, and some conclusion and future work. These buildings, we choose to analyze the most representative buildings of this typology, and we analyzed building located in aggregate due to the fact that this is more realistic case than to analyze only isolated. These buildings are with irregularities in plant and height. They are with 4 levels. External walls are built with reinforced concrete structures filled with bricks. Internal walls have solid and hollow brick with cement mortar. Facade and interior walls, as I already told, are with different thickness in the height of the building. This building have 2 types of floors: a timber floor in the front of the building, and the reinforced concrete slab on the back of the building. Also, they have reinforced concrete elements on the corner of the building and along front and back facade, and also reinforced concrete beams on the ground floor. We performed non-linear static analysis, and numerical model was defined in Tremuri program based of equivalent frame model approach. In this case, we analyzed only assessment of the global seismic response because we suppose that reinforced concrete ring beams, which exist in these buildings, prevent local response, but for sure this should be analyzed in the future. Walls are discretized by set of panels, piers and spandrels, and non-linear response of masonry panels were modeled by non-linear beams with multilinear constitutive law. Reinforced concrete elements are modeled with non-linear beams with strength criteria according to Eurocode 8 and Italian code, and floors were modeled as anisotropic membrane finite elements. We consider 2 load patterns, uniform and pseudo-triangular, and 2 types of earthquakes, as is suggested in Portuguese National Code, and 2 types of soil, B and C, since these buildings are located in these 2 types of soil. Target displacement of structure will be computed from this intersection between the capacity curve and response spectrum that represents the seismic action. Seismic demand for Lisbon is defined with 475 years return period, and structural safety is verified when a ratio between ultimate and target displacement is higher than 1. As you can see here on this graphic, for a y direction and uniform load pattern, this criteria was not satisfied. So some strengthening techniques should be proposed. Here I have presented some damage pattern where we can see that in masonry piers we have mainly flexural damage, And in masonry spandrels, we have shear damage. Also for reinforced concrete column, we can see that we have flexural damage and shear for reinforced concrete beam, and damage level is mainly between 2 and 3 and 3 and 4 in masonry elements. In this graphic, we can see that global behavior of the building is influenced by the pushover curve from the walls on the back on the building. This is due to the regularity of this building on the back due to some torsional effect. After analyzing this pattern and after we saw that criteria are not satisfied, we propose some strengthening techniques. In total, we proposed 12 retrofit scenarios. I'm going to present 4, which are the most relevant and effective. One of them was strengthening with carbon fiber mesh applied on both facade and some interior walls where extending damage was observed, mainly in damage level higher than 3. Then strengthening of the staircases with carbon fiber mesh by keeping reinforcement of the facades. In terms of reinforced concrete elements, we performed strengthening of the corner columns and columns at the ground level of the main facade but by metal angles, and the most damaged beams in the ground level by metal sheets, and strengthening of the columns and beams on the ground floor by carbon fiber sheets confinement. In all scenarios, we made connection between walls, exterior and exterior due to the fact that this building has very bad connection between these walls. These are results. Just to tell that all strengthening techniques give increment of global resistance and they're satisfied criteria from Eurocode, but still we have some issues that we should solve. This is the strengthening techniques applied on both facade and some interior walls, carbon fiber mesh. As we can see, we were fully able to remove damage from the masonry piers, and also for reinforced concrete for some upper floors. But what we can see here that we have strengthening and we have some very extensive damage on the back facade of the building. This is actually caused by torsional effect due to the regularity of the buildings and due to the fact that we put reinforcement of the main facade, so increased resistance, and we have this effect. Then we decided to do strengthening of these staircases by carbon fiber mesh, but also keeping the reinforcement of the facade. In this case, as we can see, we managed to solve these problems. We don't have any more this extensive damage. We have damage between 2 and 3. The next the strengthening techniques which we perform on reinforced concrete elements is we perform metal angles on the most damaged columns and metal sheets on the most damaged reinforced concrete beams. And here we can see that we managed to solve the problem on some reinforced concrete columns in the ground floor and also on the upper floors. Also here we had shear damage for this wall P8 on the back on the building. Now we managed to solve this. We don't have any more. One more strengthening technique which we performed, it was confinement with carbon fiber sheets. And also with these techniques shows very good results. As we can see that we don't have any reinforced concrete, in reinforced concrete columns, we don't have any damage on the upper floors, any flexural damage, and also any, for this beam here, which we have always this shear damage, we managed to resolve also this problem. Just a short conclusion. After applying all these reinforced techniques, overall structural safety of the building was always satisfied, avoiding the global collapse of the structure. The observed damage level was always we managed to mitigate. Now recommended solution always depends of cost-benefit analysis, which we are going to do for the research in the future. And one of the most appropriate recommendations should target the minimization of torsional effects due to the irregularities found in the back facade, and also should mainly consist to reinforce connection between walls, which is really important, and with as well as possible reinforcement of the facades and walls of the staircases. In terms of reinforced concrete elements, carbon fiber confinement with carbon fiber sheets is recommended. Thank you very much for your attention.
Thank you very much, Dr. Milosevic. I think we can accommodate two questions, please. Can we have them either raising your hand? Yes, Dr. Cardinali has a question, please. Could you activate your phone, please, your mic, please?
Hi, Jelena.
Hi.
Thank you for your presentation. Sorry, just a question that I didn't really understand about the strengthening solution that you applied, and I was wondering if the different strengthening solution were both applied to the masonry structures and both to the reinforced concrete structures, or in some cases they were separated, because I didn't understand about these things.
The first two, on the first two, we didn't have any reinforcement of the reinforced concrete elements. We applied only on the masonry. And then the second two, which I presented, we keep reinforcement of the masonry, and we also reinforced concrete elements.
Okay. So just strengthening. By the way, just strengthening the masonry walls, you received a relevant strengthening of the capacity of the buildings.
Yeah, and we managed to mitigate also some in the reinforced concrete elements, but of course, everything. We did that just to see what is giving higher influence. We went one by one.
Yeah. And you didn't check instead the influence of just the reinforcement over the reinforced concrete structures, if I understood.
No.
Okay. Yeah, that depends on the failure modes of the structure as well.
Yes.
So thank you.
You're welcome.
Thank you very much. Any other question? Well, don't have any other question. Please, thank you very much, Dr. Milosevic. And we go on with the next presentation that would be given by Dr. Juan Reyes from Colombia, the Los Andes University. And the title of his presentation would be Seismic Behavior of Torsionally-Weak Buildings with and Without Bar Isolators.
Thank you, Gustavo. Thank you very much.
Thank you. Welcome.
Thanks. I hope you can hear me well. So my presentation is about the seismic behavior of torsionally-weak buildings with and without base isolators. The question that motivates this research was this one: is the torsional behavior eliminated by seismic isolation systems? So in order to answer that question, we try these fixed base structural systems. That we did was to retrofit the buildings using seismic isolation. The buildings that you can see has first is 3 stories, and they have rectangular plan for the first one, and then this one have a T-shaped plan and the L-shaped plan for the last one. As expected, the first mode of the rectangular plan is in the main directions of the building, but for the other plans, the first mode will show some coupling between torsion, as here, and some translation in the horizontal direction. And here for the other building plan, we have a coupling in both motions in the X and Y direction with torsion. So the nonlinear model we built for these buildings were based on trilinear model with a strain loss for the beams. For the columns, we use PMM interaction using plasticity theory. The panel zones, since these buildings are steel buildings, we need to model the panel zones intersection between the beams and the columns by trilinear models with strain loss. So the building model looks like this one here. And when you subject it to a ground motion, you will see the very complex behavior that we have, a lot of torsion and coupling between translation and rotational displacements. You can see also the plastic hinges forming. This is the fixed base building. We are going to compare this later with the isolated building for this case. So we use for this analysis 7 ground motions. These are very high magnitude ground motions compatible with the seismicity of the site in which we located the buildings. So here I'm showing the design spectrum for the site together with the spectra for each of the ground motions and the median spectrum for all the 7 ground motions. So then we designed the isolated building. The design was based as a retrofit. So we want to retrofit these buildings that were designed with an old code using this technique. So criteria we use for this case were we try to use bearings from the industry, Lisbon, high damping rubber bearings, designed for an average pressure of 6.9 megapascals, maximum shear strain of 150%, and the design spectrum that I just showed, which has a constant velocity of 0.95 meters per second. Axial load varies, but it's around 1300 in average for the colors we have. For the building, the final devices had 50 centimeters of diameter. The thickness of rubber were 12 layers, so total of 20 centimeters. Period of the isolated building is 2.6 seconds, and the bearing displacement is 0.30 for the design spectrum that you just saw before. And for this design, we did the design for a base shear ratio, base shear between the fixed base and the isolated of between 3 and 4. This is important because later I'm going to show that the effectiveness of the system is going to be decreased because of the highly irregular plan that this building had. First, we conducted a parametric and linear analysis. To do this, we just wrote the equation of motion of a damped-based isolation system. These are very simple mass matrix and stiffness matrix, which, as you can see here, we included some eccentricity for the isolated isolation system. These eccentricities are usually equal to 0 for a regular plan building, but for a highly regular plan building that's like these ones, we could eventually have some isolations with larger stiffness so we can generate some kind of eccentricity to compensate for the torsional behavior of the building. So this is kind of the model we did first, very simple. So for regular buildings, these eccentricities are 0. For highly regular buildings, we try to compensate the torsion of the superstructure using different stiffness for the isolators at the base. So we can get actually an optimum eccentricity. If we came out with this equation here, this equation will say that if you multiply the mass by the phi of the mode you are using, fundamental mode, and the eccentricity of each floor, these are for all the floors of the superstructure, and you add to this eccentricity here, if the equation is 0, you will get an optimum eccentricity that basically will make that the rotational mass participation for the first mode is equal to 0. So here, if I change, for example, from 0, the original eccentricity of the isolation system, and it will be an optimum eccentricity here of some value, just putting some devices with larger stiffness than the other ones. So, but then when you try to do this in practice, it's gonna be kind of difficult. So to make this simpler, we decided to use all the isolators equal in all the columns of the building. So here I'm comparing the response of the base isolated building with the response of the fixed base building. In this video, you can see that the fixed base building has a lot of very high velocities, high displacements, and the isolation system will reduce those and also the damage of the building, but still you see some vibrations in higher frequencies in the building. So those are due to higher mode effects. So the first mode is gonna be treated very well by the isolation system, by the higher modes may have some kind of problems. So here I'm plotting the fixed base and the isolated systems, see the reduction that suffer the acceleration for both buildings, the B and the C type. However, the C type seems not as effective as the B type building in reducing accelerations. Also, story drifts are also reduced. But for the C-type building, the reduction is not as high as you can observe here for the B-type building. The base shear ratio, the intended in the design was from 3 to 4, but here you see ratios of 2, you know, things like are smaller than the intended from the design. Because in the design, you usually do a very simplistic model of the building. Here I'm comparing linear and nonlinear analysis. You see the linear analysis will show in general very good approach or very good approximation of the behavior. However, all these isolations in higher frequencies that you can see here are not captured in the linear analysis. So those will be will appear and will be increment by the nonlinear behavior of the structure. So in conclusion, using similar isolation for all columns of an asymmetric plan building reduces but not eliminates torsional behavior of the structure, leaving some residual torsion that gets amplified by higher mode effects and nonlinearity of the superstructure. Also, because of this, the effectiveness of the isolation system may be reduced significantly for highly asymmetric plan buildings. So that's something that we should consider or take into account, that probably the system is good and it's going to work very well, but it's not as effective as if the building were regular. Finally, this is just something that we observed in the modeling we were doing, that the flexural stiffness of the first story beams, meaning the floor just below the columns, has an important effect of the magnitude of story drift of isolated buildings. This beam should be as rigid as possible to neglect rotation of the columns at the base, because if they rotate, then drift are not being reduced as we expected from the isolation system. And thank you very much for your attention. These are some pictures of my university here in Colombia. Hopefully someday I could go again.
Thank you very much for your presentation. Somebody has a question? Professor Oren Lavan, please.
Yes, Juan, thank you for the presentation. Maybe I didn't catch it, but did you consider any damping at the isolation level? And if yes, how did you design it? Because this may have a strong effect on reducing the responses also in higher modes.
Yeah, damping was considered in the isolation system, as you remember here when I was mentioning the criteria. We use Bridgestone high damping rubber bearings. So the model for the bearings was initially a trilinear model. So the area inside the cycle will be related with the damping. We try to calibrate the computer model to reflect results available for this kind of rubbers from the fabricator of the rubbers. So yes, it was considered. It was considered just by the model. It was not like a target value that we want to achieve. It was just considered the bearings were designed just based on displacements, mainly in displacements, and for this criteria that I have here.
Okay, so it was also evenly distributed between the isolators, because they all were the same, right?
Yeah, exactly.
This may also have an effect that it's worth investigating.
Okay, yes. Yeah, thank you.
Thank you.
Thank you very much. Maybe we can pass on the last presentation, which is use of fluid dampers in order to improve the seismic performance of reinforced concrete buildings in a symmetric plane view. It will be presented by Angelos Krystallis. Are you ready?
Yes, thank you very much. So the title of the presentation is Use of fluid dampers in order to improve the seismic performance of reinforced concrete buildings with a symmetric plan view. Can I go to the next slide?
Madam.
Okay. Earthquake engineering aims at making new or existing structures resistant under seismic loads. In order to achieve this goal, various passive and active control devices have been proposed and developed during the past decades for the seismic retrofit of existing structures or the effective design of new ones under earthquake situations. One of the most popular passive control devices for buildings subjected to seismic motions is viscous fluid dampers. These devices are supplementary damping devices which increase the damping ratio of the structure and consequently the energy dissipation capacity. Reinforced concrete buildings with asymmetric plan views are very common structural systems in countries with high seismicity. In case of these buildings, the mass and stiffness centers do not coincide. The stiffness and strength are asymmetrically distributed, something that leads to the coupling between lateral and torsional components of vibration. Therefore, large rotation angles are observed for lateral seismic motion of the base, and consequently, the perimeter structural elements suffer from serious damages. In order to deal with such phenomena, modern seismic codes suggest to provide these structures with adequate and appropriately distributed stiffness, strength, and ductility. However, in case of existing buildings with high values of eccentricity, and of new buildings with certain architectural and functional needs that do not allow the optimum choice of the structural system, an alternative solution would be the placement of appropriately selected passive control devices. The present paper examines the appropriate distribution of viscous fluid dampers in order to improve the seismic performance of a structure with asymmetric plan view. To achieve this goal, a multi-story building with fluid viscous dampers of certain viscosity is considered. 4 different procedures of choosing the exact positions that the dampers should be placed in order to achieve the best seismic performance of the building are proposed. The evaluation of the building seismic performance is carried out with the aid of linear as well as non-linear time history analysis using 9 real strong ground motions, and certain conclusions about the efficiency of the proposed procedures are drawn. Moreover, a flow chart for the optimum placement of the viscous fluid dampers in case of any building is proposed. Now, the function of fluid viscous dampers is based on the principle of energy dissipation due to the flow of fluid through orifices. By this way, these devices convert the kinetic energy of the seismic vibration into heat, and then this energy is dissipated into the air. The typical form of fluid damper is shown in the figure. The activation of the dampers depends on the relative velocity between...
Can you just please increase volume because it's hard.
Yes, okay, I'll come. I will speak louder. The activation of the dampers depends on the relative velocity between the 2 endpoints of the device. The forces applied by the dampers to the structure are determined by the placement of the devices throughout the building. There have been developed several different approaches for the efficient distribution of the dampers. The basic idea that has been adopted by the most of them is the placement of the dampers diagonally between the stories, so that the edges of the devices move because of the stories' relative displacements, drifts, during the seismic motion. This approach has been proved to be effective in case of typical frame buildings. The function of the viscous dampers can be described by the expression shown in the slide, where I denotes the eigenmode to be used for the calculation of the dampers parameters. A 5-story reinforced concrete building with a symmetric plan view has been chosen. The plan view of the typical building story, as well as the dimensions of the structural elements, are shown in the figure. The design data of the investigated building are presented in your slide. The building was first analyzed and designed by means of the model response spectrum analysis as defined in Eurocode 8. Then, the non-linear behavior of the structural elements was modeled using plastic hitches located at the column and beam ends as well as at the base of the walls. The assessment of the building's sizing performance was carried out with the aid of linear and the non-linear time history analysis using 9 real strong motion pairs of horizontal bidirectional earthquake ground motions. The earthquake records were selected from worldwide well-known sites characterized by strong seismic activity, and the selected ground motions are far-fault records and have been recorded on solid type B. Four different procedures of choosing the exact positions that the dampers should be placed are proposed. The common choices that were made for all the procedures are the following. The dampers are placed only along the perimeter frames of the building, so there are 75 different possible locations along the building's height that they can be placed. The total number of 24 dampers has been chosen, since the analysis revealed that this number of dampers leads to the critical damping ratio associated with the viscous dissipation of approximately 20%, which was set as a target value. The viscosity of the dampers has been considered to be the same for all of them and equal to 2000, which is the typical value for this kind of devices. The four procedures of choosing the positions of the dampers are the following. According to the first procedure, the viscous damping of each damper was computed with that of equation 1, and using the results computed by the first eigenmode. The 24 dampers with the larger damping ratio were selected. According to procedure 2, the viscous damping of each damper was computed with that of equation 1, and using the results computed by the second eigenmode. The 24 dampers with the larger damping ratio were selected. On the figure, you can see the dampers positions according to procedure 1. According to procedure 3, the 12 dampers with the largest damping ratio according to procedure 1 and the 12 dampers with the largest damping ratio according to procedure 2 were selected. According to procedure 4, for each one of the 9 chosen records, linear time history analysis was conducted, and the maximum force applied by each one of the 75 dampers was computed. The 24 dampers with the largest applied force were selected. You can see in the figure the dampers positions according to the third procedure. The figure on the left illustrates the damping ratios of the structure with and without dampers, according to the four procedures described above. We can see that the damping ratios of the building with the viscous dampers can be up to many times larger than the corresponding ratios of the building without the dampers, depending on the mode and the procedure, on the eigenmode and the procedure of choosing the dampers position. Moreover, the above procedures have been illustrated with that of a certain flow chart for the optimal placement of the viscous fluid dampers in case of any building. As mentioned above, the assessment of the building sizing performance was carried out with that of linear and non-linear time history analysis using 9 real strong motion pairs of horizontal bidirectional earthquake strong motions. In order to account for the directionality of the seismic motions, each pair of the earthquake records was applied along 2 horizontal orthogonal axes, forming 2 different incident angles, 0 and 90 degrees, with the structural axis of the building. For each ground motion, the relative displacements, drifts, along axes X and Y, as well as the rotations of the floors, were computed as damage measures. More specifically, for each earthquake record and response measure, the maximum of the values for the 2 incident angles was considered. Then, the average of these values for the 9 records was determined according to the most seismic code positions. Let's see some results now. In these figures, the results for the drifts under the linear here and the non-linear analysis here are presented. The 4 procedures of choosing the dampers positions are presented by different colors. On the figures, we can see that the maximum drifts along axis Y determine the seismic performance of the building, since they attain larger values than the drifts along axis X. So the assessment of the efficiency of the 4 procedures will be made based mainly on the drifts along y-axis. The analysis showed that procedure 1 was the least effective in reducing the maximum drift y compared to the values of the building without the dampers in case of both the linear and the non-linear analysis. Regarding the linear analysis, the other three procedures, 1, 2, and 3, led to very similar results, reducing the drift along y-axis up to 30%, whereas in case of the non-linear analysis, procedure 4 seems to be the most effective for the majority of the stories, up to 67% reduction, followed by procedures 2 and 3. Now, with regard to the floor rotations, the results of the analysis revealed that procedure 1 was the most effective in both cases of linear and non-linear analysis, up to 50% and 75% reduction compared to the values of the building without the dampers for linear and non-linear analysis respectively. Procedure 2 was the one that led to the smallest reduction in rotations. Of significant importance is also the fact that the use of the dampers has been proved to be more efficient in improving the sizing performance of the building in case of the non-linear analysis. Now, based on the results of the study, the following general conclusions can be drawn. The use of viscous fluid dampers reduces significantly both the drift and the floor rotation of buildings with asymmetric plaving. In case of these buildings, the distribution of the dampers should also be asymmetric according to proposed procedures. The use of the dampers is more efficient in improving the sizing performance of asymmetric buildings in case of the non-linear analysis. The efficiency of the procedures depends on the damage measures. Procedures 4 and 1 led to the best results in case of drifts and floor rotations respectively. A flowchart for the optimum placement of the viscous fluid dampers in case of any asymmetric building is proposed. Thank you very much for your attention.
Thank you very much for your presentation. We have some questions. Professor Oren, please.
Yes, thank you for the presentation. I have a question. So if I understand correctly, all of the procedures are based on linear characteristics of the structures, right?
Yes, the procedures that we used for the determination of the places of the viscous dampers, yes.
So they are based on the linear modes of the structures, yes, before putting the dampers.
Yes.
So have you seen any yielding of the damped structures? Because if there would be yielding and it would be uneven throughout the plane, that would probably change the whole behavior.
Yes. We used only these procedures, and I didn't understand very well your question. If you can repeat it, please.
Yes, essentially the procedures are distribute the dampers in the structure based on the displacements of the linear modes of the structure. Linear modes without considering the dampers. Now, first, the dampers change the modes of the structures because the damping is non-proportional. And yes, then you also have yielding in realistic buildings. So do you think you could actually even improve what results you got if you would consider non-linearity in the design, and if you could consider, yes, the effect of the dampers on the actual modes of the structure?
Yes, probably it would be the case, but in this stage of the research, we tried only these procedures based on on the linear characteristics of the structure. So we must make more analysis in order to come to certain conclusions about that.
Thank you very much. Some more question? Okay, this was the last presentation for this session and last presentation for today. I would like to thank to all participants and see you tomorrow. Thank you very much.
Okay. Thank you all. See you tomorrow. Thank you for joining us. Thank you.